So whenever you find any functions, okay, now you can think, if you see any like f of x equals something, you can think that functions also you can uh, rearrange the function into a series. Okay, so based on what we have done here, for example, the tangent inverse, we can look up this tangent inverse is, this is the integrations part of this function. And this function, we can observe that this is our geometric series, right? And we can expand the series, replacing x with negative x squared, and we have this expansion. And we integrate all of this, and this become our series for tangent inverse. So in your textbook, you may have seen the 11.9 exercise that you may see some functions, and it is you are required to make a representation, okay, for the series. So what you can do is either you can directly rearrange the forms and make it the expansion, and or you can integrate, and you can also integrate the expansion part, and you can think the sum of all of this, the formula for the sum, or you can derive the functions, and you may also get the formula for its sum. Okay. So what we'll be doing now is it's actually another series. It's called the Taylor and Maclaurin. Okay, so it's another series. It takes some parts from this power series. Okay, so hopefully you can have some exercise if you want from this 11.9. Okay, let's take a look here. Now, let me write the Taylor. The title is Taylor and Mclaren. Basically, both of these are similar. Okay, but let me tell you what's the difference later. Uh, let's start writing the general power series. Okay, the general power series. C is a constant. The C0, C1, and then x minus a. And by the power series, it will be increasing in power. So linear becomes squared, become cubes. So C3, and maybe C4. And it will increase until some n power. And let me write that the ratio should be less than this. Now let me just write this as a general function in power series. Okay. Now, if we put the x equal a, then all of this will be removed, right? Will be removed. So if the FA will be on the C0. Okay. Okay, that's the first part. The second part, let's differentiate the blue color, okay, the functions. Let's differentiate. So f prime x, C0 will be removed. We will have C1, okay, and then plus. Now, because it's differentiate, the next constant will be 2C2, right? 2C2. And the x variables will be linear, right? And this also same thing here. basically you are deriving the functions, the previous functions, okay? And then plus, and still the same, it's ratio. And let's say we also evaluate at x equal a, okay? So let's put a inside, and this will be removed, right? So f prime a will be equal to C1. Now we can do this for third derivative, and then maybe fourth, fifth, but you will see there will be some pattern. Okay, there will be some pattern. So this will be only 2C2 plus. Now we are differentiating from 3C3x minus a squared. So this 2 will be going here, right? 2 will be going to the front. So it will be 2 multiplied by 3. It should be 6, but I will write 2 multiplied by 3. So you will see the forms directly. So 2, 3, C3. Okay. And then the next one, it's plus 3, and then 4, C4. And then x minus a, and then squared. And it might be, maybe the next one is 4, or maybe maybe I will stop just here. Okay. So now you have this kind of pattern. And same thing, we evaluate at x equal a, and we get this 2C2. Oh, wait. This should be second derivative. Sorry. The third derivative should be 2, 3, C3 plus. Now 2 going to the front here, 2, 3, 4, C4. And maybe plus 3, 4, 5, C5, x minus a squared, and plus da. Now you will see the pattern. Now this 2, 3, 2, 3, 4, 3, 4, 5, and then 5, 4, 6, and so on and so forth. And we evaluate at x equal a. It's 2, 3, C3. Okay. Now if you look at the pattern that we have, okay, 2, 3, 2, 3, 4. Okay. We can make some general, so based on the pattern, the n is how many order you differentiate the functions. It will be 2, 3, 4, 5, and at some point until n, and then Cn. Or you can say that this is n factorial Cn. And we can solve the Cn. We get divided by n factorial. And this formula is still valid. Okay, if you choose n equals 0, it's still 0 factorial is 1. So it's still valid if you are starting from n equals 0. Okay. Now we have this kind of formula. Okay. Now this is the Cn, right? Now let's look back at our general equation and let's substitute. Okay. Let's put this into our very first equation. So let me write. Maybe while I'm writing the equations, maybe I'll write here. So if a function has a power series, representation at A if the functions is, this is the general power series formula, and the ratio then its coefficient basically this is what we did before, and then let's substitute Cn to fx. We get fx is the sum. Let's substitute the Cn, f, and then f and a divided by n factorial, and then x minus a to the power of n. If we expand this function of x here, this will be equal. If we start from 0, so f 0, so f a plus f prime a 1 factorial x minus a plus f double prime 2 factorial x minus a plus and you may look at these expansions, and whenever you find, okay, whenever you find a function that you may derive constantly without any behavior that, oh, it will be not, it will be having like infinite derivative, then you can apply that function as a series like this. This is called the Taylor series. This is called the Taylor series. So okay, so whenever you find in maybe some models, you may have some approximations using Taylor or Maclaurin, and this is what you are doing in the algorithm. Okay, it's either some computations and you want to visualize in a function, or you want to maybe calculate in certain values with certain functions, and you want to approximate the functions with the series. Okay, it can be reversibly usable. Okay, and what's the difference between Taylor and Maclaurin is the A. Okay, so this is Taylor, Maclaurin, A is 0. The 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 A is 0. So if we change all A with 0, that will be the Maclaurin. I will explain later. Okay. But basically, Taylor and Maclaurin is the same like this. Okay. Okay. And actually, most of the cases in math or maybe calculus, maybe another part from maybe your courses, maybe in engineering math. I think Maclaurin frequently used also because sometimes the case is A is 0. A is 0. Now let's look at the Maclaurin. What I need to do is just changing A into 0. So fx will be from, let me write completely with the sum from 0 and fn 0. Okay, that's the Maclaurin. Okay, and we can expand this into f0 plus f prime 0. And if you look at the form from the Maclaurin, uh, it is obvious that it is much more usable than the Taylor, because most of the cases, the models or simulations usually frequently in a polynomial case, right? Polynomial case in which you don't really need the some part of A to make your computations easy. Okay, and this is uh, and that. Remember that the theorem, the theorem, previous theorem, what I want to emphasize is this. Okay, so first, you need to also to be careful here. The theorem is saying that if function has a power series representations, okay, at A, so that's the first case. There is no how to say that. We cannot make sure the Taylor series is equal to the functions. But if the functions has a power series representation, then we can make the Taylor series. Okay, that's for sure. So you need to make sure the function itself is a representation of the power series. Okay. What you can do is actually, aside from trial and error, you can prove the mathematical formula. For example, let me write. We know if you have a function, this is has a power series representation. So how do you know that this has power series representations? We can look at a perspective from the geometric series, in which we can see that this is x with the power of n. Right? So we know that this is a power series representation. And now, because we now have a Maclaurin series, let's try to prove. Okay. Let's try to confirm that or has a or must be a Maclaurin series. Okay, we can also confirm 1 over 1 minus x is we can also look at from Maclaurin series perspective. Okay. Now to confirm this, first we need to find all the maybe a few terms of derivative. Okay. And this will be 1, 2. This is 1. This is we want the 3. This is 1, 2, 3. Okay, so in general, we can see the pattern. This will be n factorial, and this is 1 minus x, n plus 1. And if we put 0, it will be just n factorial. Okay. And we can conclude from here, from the general formula here, we can conclude that the Cn is n factorial divided by n factorial, which is 1. Okay. Now we look back at the functions. That this is true. That it will be x with the power of n. Okay. So this is just a confirming the functions that we know before. Okay. That this is x with the power of n, but with approach of Maclaurin series. Okay. So whenever you find a functions you can think the derivative that, okay, it can be derived infinitely. You may think the series. You may think the series. Okay. And the key point is it should have a power series representation. Okay. Okay, that's the perspective that we need to look at. Okay, any questions first? Okay, if not, let me go look at another angle. Let's say we are start from e with the power of x. Okay. Find the Mclaren series. And its radius of convergence. Okay. Now e to the x is easy to describe and easy to follow the derivative, because one of the uniqueness of e to the x, if you derive, it will be just e to the x, right? So we can write that fn x will still be e to the x. Okay. So when you have f and at 0, at a equals 0, it will be e0 or 1. Okay. Now, because you have this, then you may look at the formula that from previously, and this will be x to the n divided by n factorial. Or we can look at this as its expansion. Okay. And this is, by the way, what I think I've told you in the last semester, that we can write e to the x, okay, as a series. Okay. And because it's power series, we also can observe the radius of convergence with the ratio test. Okay. And maybe using the sequence of x and using ratio test, an plus 1 divided by an. And we get, let's write the limit. Okay. And this is 0, right? 0. So the conclusion, the series what's happened with the series if it is 0? What happened of this to the series if this is 0? So what happened to the series? You know what it means? So what can we use all x? What x value should be put if you need to be convergent? That's the question, actually. And you understand that? Do you get it? Hello? From previous lectures, we are determining that which x interval that converge, right? Yeah, if less than 1, it will be converged, right? If it's greater than 1, it will be diverged, right? And now it's 0. It's less than 1, right? It should be converged. But the question is, it's not converge or diverge, but which x should be put into the equations so that all the equations true converge. It's true that it's converged. Yes, all x. Do you get it? Why? Do you get it? Why all x is true? Okay, because whenever x you put here, because the limit of n is 0, all will be 0, right? So all will be less than 1. So that's why it's converged. Okay, get it? That's from the 11.8 or 9, 11.8, 11.8. Okay. So there will be 3 possibilities. Do you remember? Only one point, all x, or some intervals. Okay. That's why it's called radius of convergence, because it has sometimes it will be having a interval. Like if you draw if you draw a line number, maybe this is 0, this is maybe 1, 2, 3. Okay. Why it's called the radius, the term's radius. Radius is like a circle, right? You have a circle, you have a radius here, right? Okay. Now, what does it mean to be converged? That maybe in some interval, it will be maybe having, oh, it's converged from half to 2. And it's like, it's converged like that. Okay. Okay. So you can imagine like a line number and the interval, and imagine like a circle. The radius is the distance, the gap. Okay, the gap. So when you have maybe you write the equations. Okay, maybe some equations. Oh, you get the ratio or the absolute value of x is less than 1/4. Then this will be r equal 1/4. Okay. Okay, which means the gap is 1/4. Okay. Okay. So you will have at least 2 cases in power series. You will be asked for the radius, and you will be asked for the interval. The interval, you may have also 4 possibilities. Either this, or include all. Okay. So whenever you find the interval from the ratio test, you need to test the, for example, okay, maybe this is like that, half and then until 2. You need to test this half and 2 into the back to the original equation. If it is converged, you need to put okay, it's include. If not, then your conclusion will be wrong. Okay, just a review from the power series. Okay, so the series is converges for all x. And if the series converges for all x, then the radius is, if all this line number is included, we cannot make sure how long is this, right? The distance is infinite, right? So the radius becomes infinity, meaning all x can be put into our equation. Okay. Now, another thing that I already asked before actually, but I haven't answered it clearly for you, is when we can use the series. Okay, let me write here. Okay. When is a function represented by its Taylor series. Okay, let me write in the next page, but the question is, it's quite interesting, okay? Because not all functions can be represented, okay? We need to confirm the function, and we need to make sure that it has power series, but how we can make sure of that, okay? One way is to visualize into a graph, okay? And we need to approximate some value. Okay, let me write into the next page. Let me write here. So before we know that the e to the x is sum of x with power of n divided by n factorial, right? Now, how we determine e to the x have power series representation. Okay, let's start from the original equations of f. Okay, in terms of sum. Okay, we have write the formula for the sum. This is from n equals 0, f n a divided by the n factorial, and then x minus a, and n. This is the power series with the cn substituted by fn divided by n factorial. And then remember, if we talk about the convergent means the fx itself is limit of sequence of partial sum. Uh, Before we know partial sum is S, but for this case, to make a difference, let's write the partial sum as T, okay, Tn. So from your notes before, if you remember that we already did an and Sn, right? The Sn is the partial sum, an is a sequence. But if we are making a sequence of partial sums, the same way we did with the sequence before, we can limit that. And of course, both of them will be convergent, right? Now, the partial sum, if we look at this T, let me write the formula. Okay, and let's just write the expansions, and let's try sum n. So if we try from n equal 1 to maybe, let's say until t3, t1 is only 1 plus x. Okay. T2, 1 plus x plus x squared over 2. Let's say 2 factorial to make it still in the factorial form. The third one is 1 plus x squared plus x cubed, 3 factorial. Okay, maybe 3 is enough to make some conclusions. Okay. So if we look at this and we look at the conditions for the convergence, the functions is the limit of the partial sums, right? If you want to be convergent. If not, then it will be infinite, right? Now, let me write fx is the sum of Taylor series if okay, this need to be proven. Okay, we need to evaluate the limit of the partial sum. Okay, if we can find this limit, then we can know that whether the functions is having power series representations or not. Okay, now let's put in some visuals to help you see what does limit means in this term. So why it's important to see this limit. Okay. Now look at the graph here. Let's draw the e to the x. Let's say that red line is e to the x. Okay. Let's write e to the x here. And this part is y equal t1 x. Okay, because it's only 1 plus x, right? So it's linear functions. And the second one is one, if you draw the curve, yeah, let's say that is our T2. Let me write this as T2x. And if you draw another one, let's draw the third. Let's say that's the third one. So the green one is T3. Okay. So from what we have drawn here, you can check also with the graph calculator if you want. T1 and then T2, T3. If you increase the order of n, this part you will see it will be getting closer. Okay, that's what this limit means. Okay, so when you are putting n, you increase the n, the graphs for t, it will getting closer to the fx. So this is how you get when you have limit getting bigger, bigger, and bigger, it will getting closer to the function. Okay, first that is the key point. Okay. And remember that limit is a concept for getting closer. It's not uh, the exact same amount. Okay, so it will have some error, right? So if we let some remainder, the error part is the difference of f and partial sum, so that we can look at it has actually some part of this remainder. Okay, and it is a good approach to simulate any statistics, any dataset amount that you have error percentage. Okay. So R is the remainder. Okay, so if the remainder, if we can prove or confirm if the remainder, the limit of remainder is equal 0, then if we limiting all the system here, then so this will be, so this will be true. Okay. So the key is to find the R as minimum as we can, as getting closer to 0. Okay. so that we can ignore it to make this come true. Okay. It's called the let me write the more official in this part. So if functions where Tn is nth degree polynomial of f at a, and if the limit of the remainder is 0 for this case for to be converges, then functions is equal to sum of its Taylor series on interval okay. So it's first you need to make sure that the partial sum is the polynomial. Okay, you can differentiate infinitely amount of times for the function for the partial sum, and you need to arrive at the conclusion that the remainder should be getting closer to 0. And another point of view from this theorem, we can also using the Taylor's inequality. So Taylor's inequality is using some assumptions and using some value to be compared with the functions itself. So if we are using some m for some interval, let's say the interval, the distance is d, and the remainder satisfy the inequality. Okay. The inequality is Rn x less than m n plus 1 factorial x minus a n plus 1. This is true uh, for the distance d. Okay. So what does it mean is if we can make some assumptions, okay, using some distance d and then some m that we can have to compare. If you can prove that, okay, the remainder is always less than this value, then uh, if the Rn is satisfied, then this is true, our assumptions at the very beginning. Okay. And if we try this inequality into some proving some functions, we can try to check. Maybe we can check the e to the x. So let's just proving e to the x is equal to some of its Maclaurin series. So first, our function is e to the x. And first writing the Taylor's inequality. So first writing the fn plus 1 x. This will be e to the x all the time, right? And if d is a positive number, and because it's Maclaurin, so the a is 0. So this should be true. And then the fn plus 1 this is equal e to the x, and this should be less than e to the d. So Taylor's inequality with a equals 0 and m is equal e to the d. Okay. So first, okay, in math or in calculus in general, if you want to prove something, the first thing you need to make is assumptions and maybe some definitions that you are going to write and confirm. First, we need to confirm that, okay, we feel like the d is a positive number, so we can restrict our formula later. And because it's Maclaurin series, so x it should be the absolute value of x is less equal d, so that if you put here, then all these e to the x should be less than e to the d based on Taylor's inequality. So we can put the Taylor's inequality with m equal e to the d. So r and x is less than e to the d. This is for x less equal d. And the m, this is works for every n actually. If you put any n, e to the d is uh, still the case, right? And now we have the limit. We now limiting our remainder. This should be equal to e to the d limit and from what we saw here, from what also we done before, this is equal 0. And it follows that because this part, we are limiting this part, it's 0, so the remainder is also 0. Follows that limit of this also 0. Okay. If you want to put the note, it's the by squeeze theorem. So all values of x, all values of x is converges. Okay. So e to the x is true that this is the power series of x with the power of n divided by n factorial for all x. Seems complicated, but this is how we are going to prove, okay, in calculus or in math in general. So first, we need to define something, and if we are going to use some formula that, for example, this case is the Taylor's inequality, we need to find the value of m. Which part of m? It depends on functions that we want to observe. For example, this case is e to the x. It's simple because if you derive e to the x, it's just e to the x. So whenever value of x, or in this case the d, if d is positive number, it will be a constant value that's still e to the d, and it will be easier to follow if you are putting in an inequality. Okay. Okay. Now I will move to some example for some function, um, and then we may finish the chapter. I will skip the applications of Taylor polynomials because I believe that is just how we are using the remainder in a more computational way, finding errors and something like that. Okay. But as long as you get this inequality, the Rn, and how you are using this, the functions is equal Tn plus Rn. I think um, you'll be using something like this in maybe like course like engineering of math, or maybe some mechanical or civil constructions courses. Yeah, maybe, or any advanced engineering courses. Okay, if you have course like that in the future, you will getting something like this. Okay. Uh, some functions uh, find the Mclaren series. So let's try from uh, for sine x. So if we are looking at the Mclaren, we need to evaluate at a equals 0. So f0 is 0. Okay. And f prime x is cosine x and we will have several terms. Let's try maybe until 4 times or 5. Maybe just 4 is enough. Okay, because 4th term, you will be going back to the original sign. Then I will stop here. Okay, let's write the series from f0 plus f prime 0. Okay, so this will be f0 is 0. So the other one, f prime 0 is 1. So it's x plus 0. So it's going to be x cubed is negative 1. Is negative x cubed. The even part will be 0. And we are going to have x5. And it will be having this kind of pattern. Okay. So positive x, negative x cubed, plus x with 5 minus x7. And the next thing is plus x9 minus 12, and so on and so forth. We can look at this, and we can arrange our sum or our formula. The bottom part is the 2n plus 1 factorial, because it's odd number factorial. And the top one will be the odd number. So x with the power of odd number, 2n plus 1. Okay, this is the sign. And if we are looking at the Taylor's inequality, if you want to observe the f n plus 1 x, since the sine or cosine, we have two possibilities from here. If you derive sine, it will be cosine, cosine, cosine. So if we derive several times, it will have sine or cosine, right? Plus minus, right? So we can having this um, this inequality. Its maximum is 1, right? Sine or cosine, okay, for all x. So we can take m equal 1 in the Taylor's inequality. So the Rn is less or it's equal this, okay, because m is equal 1. And then the limit of this is also 0. So limit of Rn is also 0. Okay. Okay, so back to what we have uh, questioned before. How can we determine whether the function has a power series representation or not, or how we can use we can use the functions as power series or Taylor Maclaurin series. The first thing is this. Okay? If we can prove this to be true, then all true. Okay, but there is um, some functions that maybe you can say it's important function in Taylor and Maclaurin, and it's always repeatable. For example, the e to the x, and then the sine, all the trigonometry, the ln, I think the tangent inverse. Let's say the important one, the x to the n, the e to the x, sine x, cosine x, tangent inverse, ln. All that functions is proven to be having this Rn equals 0. So whenever you find the questions that is actually having elements from that function, you don't really need to prove that this is 0, because it's all we are saying that it's let's say it's the important Mclaren series in terms of the functions. Okay, so I think if you see the exercise will have some maybe complicated functions, but the function itself is maybe composed of either sine, cosine, ln, e to the x. Okay, like that. Okay, another important part uh, from the Maclaurin Taylor series is this part is sine x, right? It's sine x. What if we are going to check the cos x? Okay. From what we did before in sine, you can do that part if you want. You can check cosine and then check when it's a is 0. You check the derivative. Okay, you can check how we can expand the functions. Check the formula. We get the sum, etc., etc. Right? But we can also think the cosine x as a derivative of sine x. We can also think from here. And sine x, from what we did before, is actually we can just derive the expansions. So we can derive this. So the first one become 1, and then this become 3 x squared, and then 3 factorial. And then this will be 5x with the power of 4, 5 factorial. This will be 7 x6 and then 7 factorial plus dot dot dot. And we can simplify this, become x squared and then 2 factorial plus x fourth and then 4 factorial and then 6 factorial. And we get this formula. The sign is odd number, while the cosine is even, right? Even number. Now, this is cosine x, or we can arrange its formula as n equals 0 until infinity. Yeah, it's even number now. This is for all x. Okay. Any questions? Okay, now try to find the Mclaren series tangent inverse x and ln 1 plus x. Actually, in your textbook, we have the binomial series for Mclaren series, but I will skip that binomial. Okay, I will not touch that binomial for now. Okay, I hope you can try this at home, and later I will show you the solution. But let me give you some notes for the Maclaurin and Taylor series. Okay, first is uh, you can make a new Taylor series from old. Okay, what does it mean? If you have, for example, fx equal x cos x. Okay. Cos sine x, you know this Taylor series. What you need to do is just multiply by x, right? So, for example, it will be x, and we just put the cosine. So we will have this is for all x. Or we can, or you can be like asked, uh, for example, find the function. The function represented by some so it can be reversible question. So you have the sum, but you need to be able to extract what kind of function from this series. First, we can look the sum, maybe rearrange the form. Let's put all into one bracket. This series is actually, if you remember, the e to the x is this, right? So this is, if we are looking at this two, then it's the same with x being replaced by negative 2x. So we can conclude the functions is equal e with the power of minus 2x. So either you can use uh, the basic Maclaurin series like sine, cosine. Later you can try the ln and tangent inverse. That will be your basic series for Taylor Maclaurin. And then e to the x also. And you can utilize all those basic series into more complex situations. Okay? But basically, that is all functions that we will try to observe. The geometric 1/1 minus x, e to the x. Let me write here. This is only the function that you need to be taken care of. Okay, first is 1/1 minus x. Second is e to the x, sine x, cosine x. the tangent inverse, and ln 1 plus x. So only this. Okay. The rest of the problems, or maybe the question in the exercise, is based on what this function will be utilized. For example, like you can multiply with maybe you have a tangent x. Tangent x is a sine divided by cosine. Or maybe you want to multiply x sine x or x e to the x. And maybe it will be having more complex situation. But in a way, all those complex situations is basically from or composed from all these functions. Okay? So that you don't really need to prove that the limit of the remainder should be 0. If that is the case, then you will need to like proving all the mathematical concept. But we are limited our chapters in just all these functions. Okay, so you don't need to be worried to find or proving whether it is having power series or not. Okay, because I think if you just stick to these functions, that's okay. Okay, so at your home, try to make Maclaurin series of tangent inverse and ln 1 plus x, and make the formula the sigma. So the first thing is you need to derive, maybe several times, derive, and then put 0 for the Maclaurin. Okay. And then the last part, you have the series expansion, and you need to make the formula, make the sum. Okay. Okay, I think that's it for today. Hopefully you can do all of this. Okay. You don't really need to really understand the core concept. Okay. As long as you can see the pattern from the Taylor or Maclaurin, that's enough to be remembered. For example, like this one. You are starting from this sign here. Okay. Sine, derive, and you will see the pattern. And you can put all of this, okay, all of this value into the series. You can arrange the formula. That's enough for Taylor Maclaurin. Actually, that is the most or the frequent cases for you to understand, because at least this, if you're going to continue for some courses still in advanced engineering math, you will be looking this more and more. Okay, so as long as you can arrange this, I think that should be fine. Okay, the part that you need to prove blah blah blah, that is just for this understanding. You don't really need to fully understand what is happening there. Okay, as long as you can see the pattern here, that's enough. Okay, for me that's enough. Okay. Okay, I hope you can try at your home this tangent inverse and ln. And I will stop here and see you next week. And if we finish chapter 11, I will continue chapter 12 a little bit, and then maybe before the midterm.